I'm very happy to have you first, Dr. Wassim Jabi. As I said before, he's a reader, a professor in Cardiff University. He's also the director of the program MC program for computational methods in architecture for architecture. He's very active. He also he published research, on topics ranging from parametric design to generative design, and also building a performance simulation. If you guys see me, if you saw this book, um, he is actually the author of this book, Parametric Design of Architecture, one of the first books on parametric design. It's very must for who wants to go deep in parametric design. He was also the leader of Acadia. His lecture will be on design form and design intent. It's very actually exciting. I saw the titles. It's very I promise it will be an interesting one. Okay, you can start, Wassim. If I
Thank you.
forgot something, please correct me
No, that's absolutely fine. Thank you. Thank you for the kind introduction, Abed, and thank you for inviting me to be a juror on this competition. I'm looking forward to it. And thank you, everybody.
Thank you very much.
Thank you for attending this talk. So yes, I titled this talk From Design Form to Design Intent, and I'm hoping that by the end of this presentation, you'll get a feel for what I mean by this title and why I called it that. The lecture is really a bit of a summary of what several lectures that I've been doing now for the past maybe 1 or 2 years, based on the research that we have been doing with a piece of software called Topologic. And I'm hoping to be able to guide you through the software and then tell you why it's important, what it can change, what is it that we can benefit from using that piece of software. Before I tell you about the presentation, I need to also acknowledge my colleagues, because this is a very large research project. It went over 3 years. It was funded by the Leverhulme Trust for about £300,000. So my partners on that were Dr. Robert Aish from UCL at the Bartlett, Dr. Simon Lennon, Dr. Katerina Khatsi-Vasilyadi, who was our research associate, and she's now a lecturer with us at Cardiff, and Dr. Mario Wardhana, Nicholas Wardhana, who was the main software developer. He's a computer scientist, and he's now in Japan, actually. The project just recently ended at the end of last year, but the work continues. Now, this talk, I will give you a bit of an introduction about spatiality, abstraction, and awareness. What do I mean by those? I'll explain those in the slides. Then I will introduce Topologic, which is a large piece of software that integrates geometry, topology, and semantics, or information even, if you want to make it a bit simpler. Then we'll talk about how these things can enable spatial reasoning, enable you to think about space. And then we'll conclude a little bit with the discussion of the title. Why did I call it From Design Form to Design Intent? So when we wrote the proposal to the Leverhulme in 2016 almost, and a couple of years before that, we were looking at BIM systems, and building information modeling systems are obviously fantastic. They're really a great addition to the workflows that we have. They allow architects and engineers and contractors to collaborate, to create a building, to put all the pieces of the building together, and really construct it, right, with a lot of control and a lot of logic. However, it misses one thing, and it misses one very important thing that we as architects and designers are interested in, which is the idea of space. And the idea of space is really difficult to get to grasp with, because it's not a solid thing. So a BIM system, you can say, okay, I'm going to put my foundations, I'm going to put the walls, slabs, doors, and windows, that's absolutely fine because these are solid pieces and you can put almost like a kit of parts together. But for space, which is the negative kind of leftover entity, it's hard to define, it's hard to model, it's hard for computers to think about it. So what we propose to the Liverhome is the idea that we would like to represent space in a better way in these systems. And we set out that kind of goal for ourselves. The other idea or the other kind of critique we had of BIM systems is that apart from not paying a lot of attention to space, they kind of invite complexity. They invite complexity from the get-go, from the start of the design process. And we as architects, we can handle complexity, but we also don't always have the information to create a complex artifact from the beginning. So what we do is actually we start with abstraction. We use abstraction as a method to handle complexity, where we postpone decisions, we represent things using simpler forms, more abstract ideas, and we set a strategy for ourselves before complexity sets in, before we kind of populate our ideas with actual complex building components. But what we found is that BIM systems ask you to create a very complex artifact, a set of artifacts, and then they ask you to simplify it and abstract it in order to do analysis on it. For example, as you see here for energy analysis, actually energy models are very abstract, simple models. They're actually just simply graphs. They don't even need a lot of geometry. But what you have is a BIM model with all its complexity, and then you have to kind of simplify it and abstract it. And we think that is the wrong way around. So what we have proposed to the Liverhome is we want to reverse the arrow. This is the term we use, is reversing the arrow, which we would like to have the architects focus on the strategic conceptual modeling first, and then have software, which is far more advanced than humans at this point, have the software populate these rigorous lightweight models with actual BIM components. I always say that software is very much better at humans at filling an auditorium with chairs. We don't need to do it ourselves. We don't need to waste our time filling auditoria with chairs. Software can do it for us. And the last kind of disadvantage we saw in BIM systems is that they don't always have what we call awareness. What do I mean by awareness? What I mean is that the objects that you are building in a BIM system do not always necessarily know what is going on even around them. So what you see here on the left side is an image from one of my favorite pieces of software, 3D Studio Max, and I built these cubes. But if I think to yourself, if I ask one of these cubes, who is above you, who is below you, who's to the north, who's to the south, it cannot answer that question because it is only a conglomeration or a list of objects. They don't know anything about each other. Topologic, on the other hand, the software that we created knows about these things. And when you ask an entity, it can give you back information about what is going on around it. It knows what it shares with another, what it shares with its neighbors, who's below it, who's above it, etc. It can answer spatial queries, as we call them. But it doesn't have to be that way because, as we know, BIM models are basically graphs. What do I mean by graphs? A graph is basically, a simplification is that it is made out of nodes and edges, things that are connected to each other. So in a way, when you look at a BIM model, it is a graph. Everything is connected. We know, what things are connected to what, but that information is not made available in a clear and consistent way, and you cannot ask questions of it in a clear and consistent way. So we end up having to download plugins and to kind of use ad hoc methods in order to get the information that we need out of a BIM system. When in fact, there might be a better way, which is to build a connected graph of your model so that you are always able to answer these questions in a very consistent way. So we went ahead and built this piece of software, and this is called Topologic. It uses some very simple entities, starting from a vertex. Two vertices make an edge, a group of edges make a wire. If you close that wire, you can get a face. If you group those faces, you can get a shell. And if you close that shell, you can make a volumetric entity called a cell, which is our main kind of entity that we deal with. And then if you group those cells together, you get something called a cell complex, very much like soap bubbles. They have to share faces. And then you can mix and match. You can put everything together and make into a cluster. What is really important to note here is that what I am describing and what you see on the screen is the geometry of the topology that we are representing, meaning that there is a difference. We kind of delineate a difference between topology and geometry. One example is to think about, let's say, a necklace or a chain of some sort. If you hold it between your hands, that chain has a curve to it, right? And it can be quite complex. But when you think about it, that chain has a beginning and an end, has two vertices, right? A starting vertex and an end vertex. The same thing, let's say, for a helix in space. It has a starting point and an end point. So you think of it as an edge, but the geometry of that edge could be very simple, could be a straight line, or could be very complicated as a helix or a chain. So we represent both. We store the geometry, but we also deal with the topology of it. In addition to these things, we added some really interesting, more abstract classes. One of them is called a graph. So the graph basically, and I'll show you an example of it, is the dual graph. So if you have, let's say, two cubes connected to each other, the graph would be a straight line with the vertices being the centroids of the two cubes. And I'll show you some examples of that. We added also a dictionary in order to add information to the object. So any object can have a dictionary that says who manufactured it, what's the price of it, what's the weight of it, all of that. And we added things called content and context. So you can put objects inside other objects, and you can have something exist in the context of something else. So a window can exist in the context of a wall, but it can also exist in the context of a room. So just to give you an idea of what topologic is, it's quite an extensive piece of software. It's written in C++ at the bottom, and then C#, and now we're moving it to Python as well. And it exists within visual data flow programming like Dynamo and Grasshopper, and we're also exporting it to other pieces of software as we speak. It does Boolean operations, so you can union two things, weld them together. You can subtract one from the other. You can find intersection. That's all normal, but it also does other things which are irregular, such as merging. So when you merge these two cubes together, you get actually three cubes. You get sort of like one space on the one side, one at the top, and then the small cube in the middle. That is all one entity. It becomes a cell complex, and they are all connected. So you can ask the middle cube, who are your neighbors, and tell you, oh, I have one to my side to the left and one to my right. And you can impose certain things, and you can do the exclusive or. I'll show you some examples of that. So this is the dual graph. This is an example of dual graph. So what you see in kind of this kind of dark, light gray, blue, whatever that color is, that's a cell complex. And the dual graph is the wire that is represented in the middle. It basically connects the centroids of the cells that share faces. So anywhere where there is a shared face, it puts an edge. And it allows you to do graph theory type of queries and analysis. And there's a whole field about graph theory and what you can get out of it. The content and context and custom dictionaries requires a little bit of an explanation, and I'll show you. I hope I have the video for it. Yeah, so I'll use this video to explain this, and it will repeat, I believe, this video a couple of times. So I will just talk about it. Basically, what you're seeing here is somebody who's trying to design, let's say, a building of some sort, and this person would like to make it into three basic functions. They would like to put retail at the bottom, which is represented in blue, and then put offices on top of that, which is represented in yellow, and then a block of residential units up on top. If you're starting your design, you probably will design it only with three cells, right? Retail, offices, and then residential. You don't know exactly how they're going to be subdivided, but that's how you would start. So we take that and we put three dictionaries, one for retail, one for offices, one for residential, and that becomes a cell complex made out of these three cells. After that, we take a cluster of faces and then we slice it. We call it slice it and dice it, basically. So we slice it into many, many little cells, right? It could be hundreds, it could be thousands of cells. These derivative cells automatically inherit the dictionary of their parent, of where they came from. So they know that they were part of a residential block, so they become residential themselves. So you'll notice that all these small cells now are color-coded correctly. I did not color-code them myself manually. They're color-coded correctly because they have inherited the dictionary of what they have done. What this illustrates is that you can start simple, start abstract, and start strategic, saying, this is what my intent is. This is what I want to do. I want to do a tower where the bottom floor is retail. On top of that, I want to put some offices. And on top of that, I want to put some residential units. And then you leave the detail till later, like how you are going to slice it, how you're going to detail it, how you're going to make the actual building. And that comes from topology itself, from kind of the transmission of dictionaries and semantic information through Boolean operations. We also completely resolve everything. So basically, if you have a building like this and you are imposing this atrium on it, we don't have any kind of duplication, no duplicate surfaces, no duplicate edges, etc. Why is that important? If I am trying, for example, to order from a manufacturer, I want to order my columns, my steel I-beam columns of some sort. I need to give that manufacturer exact quantities. So I can count, if I tell this, give me your edges, and from those edges, give me the columns, it will give me the exact number. There are no overlapping columns, nothing of the sort. Everything gets spatially resolved exactly as you need. In this case, I'm imposing this kind of central core on this building, and you'll notice when it reaches the middle, the central column, the central edge disappears and then reappears automatically. And that all because we do full resolution of the operation. In this one, I'm taking a cell complex and I'm asking the faces to tell me what kind of spaces they are bordering. So basically, if you look at this, I'm asking two questions of these faces. The first question is, how many cells are you adjacent to? If the answer comes back as one cell, I color that yellow because these are external or exterior faces by default. If one face has only one cell next to it, by definition, it is an exterior face. So I take all the remainder faces and I ask them, okay, so how many cells? They say, well, 2 cells, right? These are all the interior ones. But I don't stop there. I ask each cell on each side, what kind of cell are you? If the answer comes back, I'm a small office and I'm also a small office, A and B are both small offices, I color that in blue because it is a partition between 2 offices. If the answer comes back, I am between a small office and a large atrium, I color that in red, right? Because I might want to put glass in there, or I might put a different material in there. The point here is that every entity in topologic knows the situation it finds itself in and can answer that question. And therefore I can categorize and do analysis on the building based on the answers I'm getting back. So you'll notice that as this little cube is going around and changing its size and peeking out, etc., the faces that are being returned are being automatically color-coded based on the answers to the questions that's being posed to them. Same thing here, same kind of idea, but what I'm looking here is private and public. So I am saying you have private and public or dark and light spaces that are adjacent to a kind of central atrium that's passing through. And from the adjacent spaces, only highlight the ones that are public because I want to do something different perhaps with them. This one is based on space syntax. So I am building this cell complex and I'm moving the bars around and I'm asking every cell to compute its distance, its topological distance to every other cell in this building. And the ones that have the shortest distance are obviously the ones that are the most central in the building, right? Because it is very short to get to it's very quick to get to every other cell. And the ones that have the longest distances are the most isolated, the most far cells. So you color code them based on how central or not. The centrality and integration is a very standard space syntax type of measure. And if you look very closely inside this cell complex, you see the actual dual graph in terms of the edges and the lines. So you can do graph theory analysis with topologic. So we ran a workshop. I will not bother you with the details. That was part of a paper we presented recently with Katerina, where finding the shortest distance, perhaps, is affected by the topological situation and by the modeling situation. So in this case, we are changing the volume and we are asking topologic to find the shortest path between two spaces going through the smallest spaces, the ones with the least amount of volume. And why would we want to do that? That's just an example. For example, if you are routing HVAC pipes or ducts, you would like them to go through small spaces, not go through the big conference room that you spend so much time designing. So you can find the spaces that are more appropriate to route a certain thing. Or you can say, I want to take my visitors through the spaces that are labeled as public and not have them go through private areas. So the semantic information that's embedded inside a cell can inform the result of analyses. And in this one, we are intersecting two objects and we are giving two numeric values to them that will affect the intersection, that red cube that you see. So the height of that red cube comes only from pieces of information that were inherited by the two intersecting bars. So it's not about the height of it or etc. You can put an arbitrary piece of information, and just because it is an intersection, it will know where it came from, it will know who its parents are, can tap into that information and make a decision about itself. So you can mix colors, you can mix heights, you can mix widths, whatever you want. But the idea is that this kind of information flow through Boolean operations, through kind of a geometric operation. So how would we use something like this in a kind of more practical way? So this is, this is an example that I did actually yesterday and today, which is I set to myself these types of rules, which is to say a living room that intersects a kitchen gives me a certain volume. If that volume is big enough, make a breakfast area out of it. But if it's too small, don't do anything, just give it back to the kitchen, right? Because you can't do anything with a very small area. And the similar rule to when you intersect your living room with your bedroom. If that intersection is too small, just give it back to the bedroom, keep it blue, don't do anything with it. But if it's big enough, make it into closets or circulation or a bathroom. I mean, this is just kind of like a illustrative example. So you can write your rules ahead of time, and this is expressed in a Python script. And then all you need to do is insert the dictionaries in the three cells that I have. So I start with a living room, a bedroom, and a kitchen. And then I start moving the living room around and let it intersect the other two spaces. And based on that intersection, based on what was intersecting and the volume of that intersection, it automatically inserts a new dictionary in that space and says, now I am the intersection of a living room and the kitchen, and I am big enough so I can become a breakfast area. Or I'm big enough because I'm in an intersection between a living room and a bedroom, and I'm big enough so I can become a circulation/closets. At the very end, I look at the cell complex, I get the cells out of it, and I query the dictionary, and I just color code the dictionaries based on what they are saying. If it's a living room, I color it red, etc., and the results come back here. So you can play what-if kind of situations, and it will always reply. So what we have done here is that we have modeled, not the building itself, we have modeled what we want to do, which is our intent. That's my rule. This is kind of the architectural language that I have created for myself. So, just some remarks on this, that our research has indicated that topology can use abstraction as a method to address complexity and provide a formal system for creating, editing, and connecting topologies. Components in topologic have an inherent spatial awareness that enables them to intelligently react to requests and changes in their surroundings. Topologic shifts the needed information from ad hoc algorithms, like you see in BIM, like these types of add-in plugins, to formalize data structures and methods implemented using an object-oriented approach. When combined, when all these features are combined, you can enable topologic to support rigorous spatial reasoning and analysis in the conceptual design phase. And fundamentally, topologic expands the pursuit of fidelity to design form, meaning like we're not obsessed with creating something that looks like the final form, but we are pursuing fidelity of design intent. We would like to model the rules that we are implementing as designers. So what is needed? We need first to define. We need to decide on our architectural language and grammar of vocabulary and rules. We as architects need to be very clear about what is our language and what we are interested in, because that is what you are going to encode in a system. Also, you need to get organized. You need to invent ways to set out your design before complexity sets in. So you need to create a conceptual model, a strategic model, I call it, before you start simply worrying about the foundations and the walls and the windows, before you kind of add complexity. And you need to let the software help you evolve and evaluate your design. Let it, as Andrew Human from Haifa, who gave us a talk recently, he said, automate the boring stuff, basically. Let the computer do what it is good at and just focus on the conceptual aspects of it. And then, yeah, as we said, let the software help you populate and detail your design and make sure that that kind of complexity is linked to your original intent. So your shift your focus as an architect and designer shifts from design form to designing your intent. Thank you.
Thank you very much, Jabi, Wassim Jabi. And I'm very impressed. You are giving the spaces awareness, which is this is very brilliant. I mean, I hope that one day we'll come to a situation to give the machine some intuition, because because unfortunately many architects are losing that intuition today. So maybe the machine will solve this issue. I have just one question. Have you ever tried this on one project? I mean, real project.
Right. So we are still at the very, very early stages. So I mean, just to tell you a little bit, topologic is being used now in a couple of large firms, and it's working behind the scenes, so you don't see it kind of in the front. But topologic has been integrated into a piece of software. First, it was called BOM. Well, it exists at Bureau Happold. So Bureau Happold is a large engineering firm, international engineering firm. They worked on Zaha Hadid projects and other projects. So they have incorporated topologic in their building and habitats object model. And they use it exactly like I have shown to get topological information in order to create mainly energy models. So they do energy analysis because you need the adjacencies. You need to know which surfaces are between which spaces and thermal zones in order to do your analysis. So topologic is working behind the scenes doing that. Now, the engineer who worked on it, a brilliant person named Mikhail de Gunziak, he left Bureau Happold and went and worked for a company in Bristol called Horlia. And he invented a new system, very similar to BOM, but obviously kind of invented from the beginning. And he, again, incorporated topologic in doing that. Again, for energy analysis and for just resolving, they call it model laundry, like almost like washing your building, in the sense that it cleans up the model. The other example I could point to, a couple of them actually. There is an architect, a Syrian architect actually in Germany, who's using it to take test fit data, test fit models. I don't know if you know, if you have some time, look up testfit.io. They create like very quick feasibility studies of a site. So you say, I want so many units, etc., and you provide the site, and it's very interactive. So we have taken those models and we have implemented them in topologic, in Dynamo. He and I work together on it, and we can convert test fit models to Revit models now. And he worked on a real project for his architect as a feasibility study. And lastly, there is a MEP engineer. He does HVAC analysis and all of that. Sean Fruin from Sigma Delta Design. I can't remember the name of his company. It's a small company that he runs. And he uses topologic for analysis of MEP systems in real projects. So finding the shortest way to route HVAC ducts and doing analysis, and modeling, and he moves it to Revit as well. So these are some of the examples. Obviously, they are very, very practical. I would love to see it used by designers in the early stages as a conceptual tool, and I'm yet to see that. Obviously, it's growing, every day.
Yeah, it has actually a huge potential. I have other questions, but I will give the people to ask Salim, Dr. Salim.
Okay.
Can you? Yeah, okay, we hear you.
Yes, thank you, Wassim, for this interesting presentation. This software reminds me with the ArcMap GIS when I used to illustrate for the students about the difference between AutoCAD and GIS, that GIS can talk, you can interact with it. It knows topology, it knows distances, what's nearby you, the neighboring versus the neighbor. When you do the query, it's a smart software, while the AutoCAD is drafting software. This software is smart, but my question is, so it's more, as you said lately, it's more conceptual. It talks about function rather than the form. Is there any interaction between form and function in this software? Thank you.
Sure. I mean, first of all, definitely the engine behind topologic is very similar to GIS engines. There were systems that were doing very similar things also in the late 80s that went by the wayside and were not incorporated. So when things like AutoCAD and 3D Studio Max and then Revit and all these pieces of software came about, they removed what is called non-manifold topology. It's a type of way of representing space that has topological information built into it, and you can also subdivide spaces on the inside. So you can have a cube with a face on the inside, which you cannot easily do in other software and keep it going. So definitely the heritage of topologic is based in these systems. So you're absolutely correct to talk about GIS because it does it at the urban scale, and we are doing it at the architectural scale. Now, when you're talking about does it interact between form and function, yes, absolutely. I always show, and this is probably a strategic mistake on my part, because I always show very simple cubes, very simple shapes, so that I can explain the concept. I usually use these for my students. So I'm trying to explain them very, very quickly. But topologic is capable, like any advanced 3D modeling software, because it's based on Open Cascade, it's capable of very, very sophisticated formal manipulation, NURBS surfaces, NURBS forms, etc. It's based on what we call boundary representation, or BREP. And if you know BREP, like for example, if you're an industrial designer and you're doing a very complex widget of some sort with very curved surfaces, etc., that kind of representation it can handle. But yes, I think we should probably do more examples that are bigger on form. You can find some examples on my YouTube channel where I have taken, let's say, twisted tower, and I do energy analysis on it and things like that in topologic.
Anybody else? Guys, you can ask, by the way, on the program. It's okay. On the program, I mean the university program. If anybody looking forward to start any master program in computation, you can ask. This is the opportunity. Yes. Many people ask me, how can I contact Dr. Wassim Jabi? This is the opportunity now. You can talk with him now.
I'm happy to tell you about our MSc if you'd allow me to. Just it is a one-year MSc at Cardiff University. It is based on the concept of algorithmic thinking. So rather, we do digital fabrication and form finding and all of that, but the unique thing about it is that it teaches you how to build your own design tools, and it teaches you how to do scripting in Python in order to build these tools. So a lot of people tell me that it's quite unique, especially in the UK, because all the other programs really it's more about like form finding and digital fabrication and just general use of software and Grasshopper, but really it doesn't go into the algorithmic thinking, into like a more deeper type of stuff, where increasingly you're finding big architectural firms and progressive architectural firms are asking for this kind of expertise. They are not happy to just have somebody be a Grasshopper wizard. They are actually looking for somebody who can build new tools and new plugins on top of things like Dynamo and Grasshopper, and use machine learning and use artificial intelligence for these things. So we touch upon a lot of these things. And it allows you to also be in charge of your teaching and learning, so that there's a dissertation that you have to decide on yourself in consultation with your supervisor, but you are following an independent program, independent brief. So yeah, people like it. It's a quick one year program. So if you are interested, definitely come in touch with me. I want to take a second to say hi to Suha Becky. She said hi on the chat. Really good to see you again, or at least to see your name.
I didn't see the chat. Okay, it's for you.
Just saying how is that? Yeah, there's some familiar names. I think I know some, few people.
Okay, guys, questions. Okay, I will ask another question. Sorry.
Sure.
Actually, this is topologic is really, I can see the potential. I can now use my imagination and see, the usage or the implementation on other expertise or disciplines. My question is, have you ever thought that maybe experiencing, because it's kind of awareness, but if you put another parameter of UX, the user experience, do you think that in forthcoming 2 years, can this program topology can also examine the UX at the same time?
That's a really good question, because we as a team, we've been thinking that actually topologic right now feels a little bit almost like as if it's in prison, because it is right now encapsulated inside Dynamo and Grasshopper only. And obviously topologic itself is a foundational software. It has a .NET version. Now we're moving it to Python, where it's a C++ open source. So you can take it and put it in different engines and different environments, and you can expand it to look at other issues like UX, like even in architectural domain. So when we were talking about topologic, we talk about it almost as a foundation of capabilities, and we were waiting for people to take it and say put on top of it domain specific logic and domain specific information. So to say, one interesting question would be, how can you improve the spatial experience of somebody inside this building? Can you design something that talks about spatial experience? Now I'm going to point to, maybe I will embarrass him a little bit, but you really guys should take a look at the dissertation of Amer, who's here with us. Amer was my PhD student. He, unfortunately for him, he finished his PhD before we were able to offer topologic to him. We were developing it and discussing the ideas with him as he was developing his dissertation. But in his dissertation, he actually, if I can summarize it in one point, is that he can give you information about at least the social sustainability of a building by how it is constructed, which is a very, very difficult thing. To say that people are going to have their children play with other people's children in the courtyard to kind of be able to give you information as a designer that actually, yes, if I have small children, they will be able to interact with other children. They're not going to be isolated. Or this building does respect the social norms that I have to live by. It does allow neighbors to help each other, or it does allow for privacy. He was able to tackle these questions through a study of the topology, the geometry, and a lot of analysis on what he is creating, and to be able to also optimize them. So, I mean, as I said, what would have been really fantastic if he used topologic itself, but he was using topologic concepts in that dissertation anyway. So I'm optimistic that it can answer more important questions than where do I move my HVAC pipes? You know, where do I put my HVAC ducts? That's a bigger kind of goal for us, definitely.
I see. Okay, guys, I don't see any other questions. Still people coming, but we are at the end. I have one question.
So Wafa is asking a question in chat. Which program do you use for space?
Yeah, you can read it. Okay.
Yes, I can read the text.
You can see it.
Right. So in Amer's dissertation, he obviously used space syntax software like depth map and agraph and all of those. For topologic, what you saw as space syntax analysis, like, for example, centrality, vertex centrality, or space centrality, we wrote our own because topologic can do it. So we have been able to just simply compute the topological distances, aggregate them, and then do the color coding based on that, fully three-dimensional. When we are doing, for example, shortest distances or isophysts and stuff like that, it's written inside topologic. We write the code in Python ourselves. We don't use a third piece of software.
That's a question from Wafa Suleiman. People, any other questions?
Yeah, I have one question. Thank you, Wassim, for this amazing lecture, and also it was a very nice experience for you in my PhD journey. My question is that one of the disadvantages of space syntax is only 2D analysis. So this software can analyze the three-dimensional. For example, if we have a double volume or a courtyard between 3 or 4 floors, so can we do the space syntax analysis for the third dimension? Or
yeah, 100%. At least some types of space syntax analysis, like, for example, the integration, the spatial integration, is done completely three-dimensionally. We have done things like the isophysts in 3D, but it takes a lot of time. Obviously, it is very compute intensive, so it kind of is difficult to do three-dimensionally. But for example, if you not so much space syntax, but analysis in general. For example, Revit and Autodesk recently announced that they can do pathfinding. Right, you can find your way from one room to another room. What they do not tell you is that you can only find your way from one room to the other room if they are on the same level. So you cannot really find yourself from one office to one office below and go down the stairs. So what I did as a challenge is I took a Revit model and kind of processed it through topologic and wrote a script that can find a three-dimensional path from one space to another space, and it will go down step by step. It will actually climb down the stairs or go through an elevator correctly. As I said before, BIM models are graphs and they have all the information, but somehow, for some reason, software developers don't take the time and trouble to actually take advantage of that information. But if you do it, actually the information is right there. You just have to build correct graphs or correct models that allow you to do these types of analyses. And that's what we aim to do with topologic, is that we wanted to design something that is in a way Puritan. It's in a way it's brittle. It's kind of doesn't compromise a lot. It has this kind of disadvantage to it, but it's built according to pure concepts that we thought are going to be needed later on. And I think we've proven to ourselves that that was the right way to do it.
Okay, thank you.
Okay, anybody else?
Can I have a question, please?
I did not put him up to it. This is Anas, another of my PhD students. But go ahead, Anas.
It's not about the space syntax. It's a little bit less jargon question. It's just it's something we usually, people who deal with computational, gets to be asked a lot. And actually spending 5 years with Wassim, I have never asked him that. So it's a good time to do it. So do you think that computational design in general will be a success story in the field of practice, other than not just the global north or the global west? I'm talking about the Middle East and the global south and east. Do you see this computational methods being applied in outside the big firms and the big names and Rumble and these kind of stuff? We saw BIM coming into the market in general, but still BIM didn't penetrate the mid-level and low-level, even in the global south, even in Europe. And do you see computational methods like space syntax, whatever they use, Grasshopper, whatever the tools, whatever the methods, but do you see it happening outside the echo chamber of the big firms and the big names?
Yeah. Thank you. Thanks, Anas, for that. It is a good question, because when about maybe more than 10 years ago, when I was starting to experience how people who are outside academia starting to use academic tools. These are people who have graduated from master's and PhD programs, and they started going into practice and using it. What I noticed is that it was actually the small firms and the one-person firms who are using these innovative tools. And they were doing that in order to gain an advantage over large firms who had a lot of resources and were able to get these things done. So by using computational tools, they were gaining a lot of modeling and analysis and digital fabrication. So you could take a look at a lot of examples of people entering competitions when they were actually doing it from their bedroom or from their garage, and they were using computational tools in order to compete. And they looked bigger than what they are. They looked competitive with large firms. So computational methods allow them to do that. Now, once the large firms caught on and they started kind of gobbling up everything and doing everything at a massive scale, it became difficult. So you need to kind of distinguish yourself. So right now, you cannot distinguish yourself by doing amazing renderings. I mean, you can outsource that to India and they'll do amazing renderings for you. So that's no longer an issue. So what is left? What is left is your ability to tell your clients more information about their design than a regular architect, like without using these computational tools. So if you are able to tell them, for example, that 90% of the units in your tower will have an amazing view of the river, because you can do visual analysis and you can do view analysis, that's an advantage, right? Now, sooner or later, these types of methods will be made available. So right now we are collaborating with a very innovative company called Haifa, started by Ian Keogh, who invented Dynamo. And what he's doing is saying, you software developers, give us your best functions, and we'll put them on the web and connect them to each other to make workflows so that you can share your expertise. And they're hoping to be able to compensate computational designers for anybody who's using their function. So if I write a function, put it up on Haifa, and somebody uses it in their workflow to do topologic analysis, for example, my company, not that I have a company, but my company would be paid. So the idea is that you are going to be in a different marketplace in the near future, where you are not providing services, you're not providing design services, you're providing computational methods as a deliverable, as an actual product that you sell. And these are contained modules that you put together. So there's a whole new bright future, I believe, for computational designers beyond AEC. I mean, beyond just simply working in a large architectural firm.
Thank you.
Thanks, Anas.
We have from Musab Widyan another question. It's a general question about the PhD studies, if you can read it.
Sure. He says, thank you for this presentation. I would like to ask if anyone wants to complete PhD in digital fabrication or artificial intelligence in architecture, what is the basic knowledge that I should, I guess, take or acquire to increase my chance to be accepted? So, I mean, Anas will attest to that because his dissertation actually included a big portion of machine learning. And he did not know machine learning, if am I correct, Anas, when we started. I did not know machine learning when we started, and we taught ourselves, basically. It's not about basic knowledge. Basic knowledge would be, for me, not so much the techniques, but actually reading around the subject, making sure that you know what has happened before you started your PhD, so that you don't reinvent the wheel. This is my litmus test when I am accepting somebody for a PhD, is there a good chance that they will make a new contribution to knowledge, or have somebody else done it before? And if the answer is somebody else has done it before, then forget it. So what you really need to do if you think about a PhD is make sure you do your homework on the literature review, on precedents, making sure that you know the field very well. You don't need to understand every detail of it, but at least understand who has done what before, so that what you write in your proposal has the potential to be new and significant. Now, then you have 3 years to do it, which is unlike the US. I mean, I prefer the PhDs in the US, to tell you honestly, because you take a longer period and you study, you take courses, you take modules, then you do a research proposal and the research practicum, and then you start doing your dissertation. In Europe and in the UK, it's very fast. It's 3 to 4 years. So you need to be ready to learn in the first year and then start implementing in the second year and then write up in the third year. Now, I know what you're asking in terms of like what skills, etc. If you are talking about digital fabrication and AI, it's a hot field, obviously. It's very difficult because we are talking about recognition. You're talking about robotics. We have a robotic arm at Cardiff, obviously, but we have not really dealt with integrating it with AI. But we're talking about an AI system that recognizes what it's producing and can make real-time decisions to change the course of action. And that is quite challenging and quite difficult. But AI and digital fabrication is an interesting field. We can do also a PhD in one or the other.
Okay, guys, I think we want to thank now Wassim Jabi, Dr. Wassim Jabi. Thank you very much. We are really thankful, appreciate your time, and it was very helpful and inspiring, by the way.
Thank you.
Because I learned now many things that I didn't actually had the chance to think different and how to deal with problems, solving problems. This is my side. I'm very sure that people also benefited from this. Thank you, guys, every one of you. Really, it was joyful, and hope to see you in the next lecture next Friday. Thank you, Wassim. Thank you very much.
Thank you, everyone. Thanks for inviting me.